Welcome to ECEN 215 Principles of Electrical Engineering. Today we're going to talk about frequency response. So let's go ahead and get started. So first, let's talk about a thing known as the Fourier series. So Jean-Baptiste Joseph Fourier came up with the concept of the Fourier series that he showed that many functions can be represented as just an infinite sum of harmonics, basically an infinite sum of sinusoids that can have different frequencies at different harmonic, at a n times the frequency, just, you have 10 hertz and then 20 hertz and then 40 hertz, so on and so forth, at just an infinite sum of all of these harmonics. And he called this the Fourier transform. So mathematically, it looks like this. We have this signal S of t um, here, and it's, as you can see, it's just the sum of some amplitude A of n for this particular cosine with a 2 pi mt, where m is 0 to infinity over t. So we have this frequency component, and it has a different amplitude for each one of these. And the idea is you end up with between A and B, and of course this changing value of M, you end up basically being able to replicate any signal with just different sine and cosine components. Now, what is useful about this, as you can imagine, now that we've kind of explored doing AC signal analysis, is that everything we have just learned about AC signals, doing the circuit analysis on it, we can now do that with any type of signal being employed, whether that be a square wave, audio, it doesn't matter. Video signals, pressure signals off a pressure transducer, temperature signals, whatever it may be, we can replicate that signal as just an infinite sum of sinusoids and just basically use this principle that we've learned using phasors and now apply that circuit analysis method to all of these signals. So let's take a look at a graphical example of this instead of just looking at the mathematical representation. So if we have a musical waveform here, say this was just an audio track off of, say, an MP3 file that you're playing off of your iPod or something, off of your phone, and you have it being amplified and going into an amplifier and then eventually to a speaker, and you were looking at the signal and it looked like this, obviously go, well, how am I going to do an analysis on whatever circuit it is if the signal originally looks like this? However, we can represent this signal actually by, again, this infinite sum of all of these different harmonics. And so we have a low frequency signal here. Notice this sinusoid in here. And then there's a little bit of a faster one. And like this here one is like double the frequency. And this here is quadruple the frequency. And they're all at different amplitudes. So you could represent this signal by the sum of all of these different AC frequencies. Now, part of this class is we're introducing you to the concept of Fourier analysis. We're not actually going to do the Fourier analysis. That's actually a little more involved. It involves Fourier transforms. So mathematically, we would spend weeks going over Fourier transforms. But what I'm trying to show you here is conceptually, we can take any waveform, like your music waveform. This applies also to video. It applies to any other sensor technology in which you have any interesting waveform where you're going to have peaks and valleys, and you can represent that as just a sum of all these different sinusoidal components. Now that we have actually done AC analysis, we can come back and apply what we have already learned to these different signals. So that's the power of that. To continue on with this concept, we have a digital waveform here. As you can see, this here would be an ideal square wave digital, and we're going to be covering digital in a later topic. But if we have a digital waveform here where we have 0 volts going to, say, some positive amplitude A in this case, but it could be, say, 5 volts, and then we have minus 5 volts here, and so there's effectively two states, either +5 or -5 or plus A and minus A. And it's just going back and forth at some period T. So we have this frequency here that we're constantly going back and forth as a square wave. Again, you can represent that signal as an infinite sum of sinusoids. And it takes a lot of sinusoids to create a square wave, but you can do it. You have the base frequency here. This will be at 1 over T for the frequency. So the you have the key, harmonic, the base harmonic sinusoid here. But obviously that one by itself just creates a sinusoid. And then you have another one that's, again, double the frequency and quadruple the frequency, so on and so forth. Again, it takes a lot of frequencies of sinusoids to end up creating the actual square wave. But mathematically, it can be done, and in principle, that's what we actually see on the oscilloscope. You can actually see as a signal goes through the different components of different circuits that we use for filtering and controlling and working with digital electronics. You actually see these high frequency ringing on the oscilloscope. So here's just some common signals and their frequency ranges. For example, the electrocardiogram, which is used for determining signals from your heart, has a frequency range of all the way down to 0.05 hertz. So very, very basically near DC. And then we all the way up to 100 hertz. Obviously, our audio range is anywhere from about 20 hertz to 15 kilohertz, and of course, and then there's ultrasonic beyond that. AM radio broadcasting is 50 to 1600 kilohertz or 1.6 megahertz. Component video signals for high definition is anything from a DC offset all the way to 25 megahertz. Frequency modulated radio broadcasting. So again, this is not a signals class, but radio that is transmitted to, like in your car or whatever, uses two different techniques. One's amplitude modulated and frequency modulated. And then modulated means you're doing one type of transform to the signal and imposing the actual signal that you're wanting, in this case audio, being transformed to a higher frequency to transmit it. Again, this is not a communications class, so I don't expect you to completely grasp that, but these signals actually operate at a much higher frequency, but you're transmitting, in this case of FM and AM, you're actually sending audible signals, but at a higher frequency. And so again, FM radio broadcasts at the 88 to 108 megahertz, substantially at a higher frequency than amplitude modulated signals. Your cellular phone, your smartphone, the bands are typically anywhere from 800 to 824 to 894 megahertz, and are now pushing in almost to the 2 gigahertz realm. Now with Gen 5 signals that we have today, probably I think those are in the 5 gigahertz realm. Satellite television, which is known as the C-band, which is basically, this is all in the microwave realm, is 3.7 to 4.2 gigahertz. And same with that's actually the C-band. This is the old large satellite dishes that I would have grown up with and had actually remembered my grandparents and, or actually not my grandparents, but my great aunt and uncle. They actually owned one of these old C-band, these are the 6-foot wide diameter satellite dishes, which was a big thing back in the 70s and 80s. If you had if you lived out in the country in a rural part and you did not have cable, but you had a satellite dish, this is a big deal. For the last pretty much 25 years, we've had digital satellite television. This is one you commonly see on the side of a house. It's about a foot and a half wide diameter dish, kind of elliptical in shape, parabolic in nature, and these signals are actually in the 12.2 to 12.6 gigahertz realm. Again, we have all of these AC signals that are coming through. All of these are sinusoidal signals ranging from these frequencies, all coming into a receiver and going through all these different stages of filters, amplifiers, and other subcircuits to finally being processed, in a case like digital satellite television, being processed by a computer, where we go through a thing known as an analog to digital converter, and we'll be discussing that in a later lecture. where these signals are converted from an analog voltage like 3.1 volts to an actual number that the computer can then process digitally. So that is why we have studied and have kind of stair-stepped our way through DC analysis, which is still incredibly important because a lot of stuff operates at the DC realm, all the way through AC circuit analysis. And really, once you've mastered AC circuit analysis, you have all of these signals and anything else you can imagine are now you can do an analysis of because everything can be represented as sinusoids. So what is frequency analysis? Well, so far in our circuit analysis, we've been looking at inductors and capacitors. Of course, resistors are just the impedance of resistor is the resistance, so that there really is no frequency component of an ideal resistor. But obviously with an inductor, there is. You know, the impedance is J omega L, and of course with the capacitors, ZC is 1, minus J1 over omega C. Now the key thing here to realize, and I'm just going to kind of highlight that here, is this concept here that we truly do have a frequency component. We have the omega here, and over here we've got this omega. So as omega changes, the impedance changes. Now everything up till now we have not really paid attention to what the circuit does. We have been given a circuit and we've been told, Vs is equal to 100 volts, times the cosine of 100 pi t plus some, say plus 30 degrees. We've been given this as our input, where we have this signal here, 100 pi is omega. So omega here would be 100 pi radians per second. Well, the deal is we now have that was at a set frequency, but now if we have say electrocardiogram, or we have a pressure sensor coming in with a pressure does something like this, and then comes down and does this, like I think in an earlier lecture when we were introducing the class, for instance, engine knock, for instance, where you have the different pressure sensor and you can actually see the knock on a piston, that kind of idea. That can now be represented as all of these different sinusoids at different frequencies, so on and so forth. So because of that, omega now is changing and is no longer static. Now the analysis, if you will, the formula of the analysis has not changed. You would still write everything now in, say, terms of ZL and ZC and of course ZR, but the actual value of the impedance now changes because of omega here. That is what's changing in our analysis. Because of that, we have to have a way of determining what does the circuit do as frequency changes. That is known as frequency response. If I build a circuit, and just to kind of draw it here before we go on and talk about networks, if I have say an inductor and a resistor, just this real simple RL circuit, right? And I've got, two terminals here, and I'm going to put some sort of waveform as the input. It's going to have a sinusoid here, and then we have our output here, and we are going to put this, and we're going to measure, the signal output, V out here. So this is V in, this is our signal input, and this is our signal output. And the question is, what is V out given a certain V in? Well, everything, again, what we have talked about so far in AC signal analysis, omega was constant. Like we just talked about a moment ago, we had this at 100 pi, which would be equivalent to 50 hertz. And again, just for review purposes, omega is equal to 2 pi f, where f is frequency. So f is equal to, say, 60 hertz, so on and so forth. This would be equal to 2 pi f, so radians would be 120 pi. So just as kind of reminder of this is something that's easily overlooked if you're in a hurry. So make sure that you pay attention to that. Um, so now frequency or radians per second, the frequency of the sinusoid here is now going to change. So, if we have a circuit here, what we got for V out is now completely dependent upon what omega is. Now, conceptually, ZL, as omega goes from 0 hertz to infinite hertz, what happens to Z of L? Well, Z of L goes from, so we have Z of L is equal to J times R omega, which is 0 times L. So let's pretend that we have 1 Henry, just to make the math easier here. Obviously, this is equal to 0 ohms, J ohms. And of course, so that's ZL at omega equals 0. And ZL at omega equal infinity, we end up with J omega, L, which is, J. Here, let me correct this here. Let's make this correct. This becomes J infinity ohms. And of course, if omega was something in between, for instance, at 100 pi would be J omega pi, ohms. And this is where omega equals 100 pi. So we know all of this. So obviously we have an increasing Z of L going infinite, as omega increases, the circuit increases. Now, if this was a resistor, and this, obviously this was a resistor, say this was 1 ohm, for instance, what would be happening here? So V out, as omega is changing, let's just say V in itself, the actual magnitude was 1. So at omega equal to 0, okay, your Vn is 1 volt. Basically at that point it would be DC. So it's 1 volt DC at if omega equals 0, and we have Vn equal to 1 volt. V out in this case would be equal to, because this is a voltage divider, is equal to 1 volt, because this right now is 0 ohms. So this basically is effectively a short. So we have V in just tied to V out. And that's exactly what we would expect on an RL circuit. If we did this DC steady state analysis on it, remember inductors become a short. So this makes perfect sense. If omega is 0, we have that. Now let's take this and let's go back a little bit. What if omega is equal to infinity? So excuse me, I'm already doing the Z of L. So if omega is equal to infinity, say hertz or radians per second, let's just keep it in radians per second. Now Z of L is equal to J infinity ohms. This is supposed to be infinity here, which means what? That means V out is equal to 0 volts. And the reason for that is now this is now an infinite resistance, if you will. The impedance is infinite. So no signal can get through between V in and V out. So what we end up with is a circuit where as frequency increases, the signal, the V out, goes down. So if we came over here just off to the side, and we made a little plot of V out over V in, we would see something that looked like this. We would end up with a signal that was decaying. And rephrase it. This is V out over V in, or V out, excuse me, I'm getting this kind of messed up. Then where this is omega. So we have V8, V out starts out at full voltage, but as frequency increases to infinity, we end up being 0. So that's fun to me. I know I've had a long explanation on this, but this is the concept behind frequency analysis. As you're going through here, and as we're looking at a circuit as omega changes. So let's just keep on going a little bit further. So this brings us to the concept of a filter. So as we were just showing in the previous slide, we had an inductor and we had a resistor circuit, and as the frequency, we swept the frequency from 0 radians per second to infinite radians per second. The output voltage with just a set, normalized input voltage, the output voltage went from equal, 1 volt all the way down to 0 volts. In other words, we went from maximum amplitude all the way down to just no amplitude whatsoever. It was completely cut off. If we put a capacitor in there, we would get the exact opposite effect. We would start out at 0 volts and we would eventually be equal to the amplitude of Vn, which is just say for argument's sake was 1 volt. So we have an input signal Vn, we have an output signal Vout. So we could call this as an input port and an output port, and we have some sort of device in the middle, whether that was an inductor, capacitor, an RLC network, something, some component or components are in the middle of this device, changing the output versus the input based upon frequency. This is known as a two-port filter network. The name comes from the fact that you have one input port and then one output port, hence 2 ports. So some common types of filters are the low pass filter, which we were just looking at. So you have a set frequency in, you have all sorts of different frequencies that could be here, and the low pass filter only allows the lower frequencies coming in from the signal. So say DC through 100 hertz passes through, anything above 100 hertz gets cut out. Then you have the inverse of a low pass filter, which is the high pass filter, which allows everything above a certain frequency to pass through to infinity. You have a band pass filter, which is, and I'm going to show all these graphically just a little bit, so if you're interested. A band pass filter actually only passes a certain band of frequencies, a lower, starting band to an upper band. Anything below the lower band is cut out. Anything above the higher band is cut out as well. It's only a little range of frequencies that is passed through. And then the inverse of that would be the notch filter, or also known as the band reject filter, where all frequencies up to the cutoff point, the lower cutoff point, is passed through. Then you do not pass through the range of frequencies you've specified, and anything above the basically high cutoff point, you then pass through to infinity. So it is known as a band reject filter, and we'll go over each one of those in just a moment. So a transfer function is just a relationship between the output to the input based upon frequency. Because in the end, we've got this network here, and we just want to have some way of relating the output to the input. So the input amplitude and its frequencies are an unknown, but this is a known network. We can actually compute the components of this network, the impedances, and come up with what's known as a transfer function relating output to input. So we label that H of F, with F being the frequency, and it's just simply V out over V in. So conceptually, if you know H of F, you can determine V out by simply multiplying V in times H of F. And inversely, if you happen to know the output, you can also determine the input by just simply doing the same thing, just reverse the math, and we have V out divided by the transfer function gives us V in. So simply knowing the transfer function allows us to know the behavior on both sides of the network, the input and the output. So here's just a simple example. If given a transfer function that is defined by this graph here, so we don't have a mathematical equation, though you could work one out because it's just simply a line with a discontinuity in this case, and the phase angle here. You can actually determine, given a phasor input, you can actually determine what the output is. So we're given H of F, both in magnitude and in phase, and we are also given Vn of F. So you're asked to determine what is V out of T. So both a frequency as a phasor and as in a term of a cosine term. So we have here, we got 2 volts at 40 degrees at 1,000 hertz. So at 1,000 hertz, we have a transfer function of a magnitude of 3. And that's simply at 1,000 hertz, so that's where we intersect. And at 1,000 hertz, we have a phase shift of 30 degrees. So that's our H at 1,000. So we have 3 phase 30, and we have 2 phase 40. So using the math we just had a moment ago, all we need to do is multiply these two together to get V out. So let's go ahead and do that. So V out is 3 phase 30, H of F, times V in, 2 phase 40, which gives us, using the math we've learned in phasors, gives us 6 phase of 70 degrees. Now that we know that, we can get V out of T, which is just simply 6 cosine 2000 pi T, or 1000 hertz, plus 70 degrees. Fairly straightforward to do. If you are given both the magnitude and the phase of H of F in terms of frequency, you can solve for V out. And of course, you can do the inverse of this if you needed to. If you were given 6 phase 70 using, at 1000 hertz, you would just do the division of this, so you would do 6 divided by 3 gives us 2, and then 70 minus 3 would give us 40. So you can see how it works both directions. Okay, let's look at another problem here. So here we're given H of F, again, both in magnitude and phase. So let's take a look at that. So we have H of F given here. At 0, it is 0 hertz. It's a magnitude of 4. 1000 hertz, it's a magnitude of 3. 2000 hertz, it's a magnitude of 2. And then here at about 2500 hertz, 2.5 kilohertz, it drops to 0. And then we have the phase shift starts out at 0 degrees, and then at 1000 hertz it's 30 degrees, and then at 2000 hertz it's 60 degrees, and just keeps going up from there. And about 2.5 kilohertz again, looks like it goes back to 0. It doesn't show. So of course the range that we're really interested in is up to 2000 hertz, similar to the previous problems. We have 4000 pi t. So let's go ahead and figure out what we have here. So we have V in is 3, so that is a DC term. Notice it has no cosine component, so this is a DC voltage. We have 2, magnitude of 2 at 2000 pi t. This is 1000 hertz. And then 4000 pi t is at 2000 hertz. This one has no phase angle to begin with, and this one has a minus 70 degree phase angle. So let's go ahead and write out what our HFs are at these various values. So let's go ahead and do that. So I'm going to start up here, and I'm just going to write what is H at 0. Well, H at 0 just simply is the 3, the 4 that's right here at DC. So let's go ahead and write that. So that's equal to 4 volts per volt, and it has a phase angle of 0 degrees. We have H at 1000 hertz, and that is equal to this intersection point here, 3. So we end up with a magnitude of 3 with a phase angle equal to 30 degrees. So we have that. And then we have H at 2000 hertz, which again here we end up with 2, because of the 2000 and the 2 intersection, and 60 degrees. So we end up with 2 magnitude with a phase angle shift of 60 degrees. Now that we have that, all we have to apply is the equation again. V out is equal to H times V in, and these of course being phasors. And of course at this point, our V in at 0, the DC component is the 3, which is, so that's just 3, and there is no phase. I mean, this is just 3 DC. So that will be simply 3 times 4. Then we have V in at 1000 hertz. And that is our 2 cosine 2000 pi t with no phase angle. So let's go ahead and write that down. Let's see here at 2 phase 0 degrees. And then we have Vn at 2000 hertz, which is equal to, so we have 2000 hertz, we have 1, because that's just implied, because there's nothing. So we have 1 volt at minus 70 degrees. So now if we go ahead and multiply these through, we end up with V out equal to 12 volts. No phase. This does not have an AC component, it's just strictly DC. We have V out here, 1000 hertz. Just for space, I won't write the 1000. We have 2 times 3, so that's 6 with 30 plus 0. So we end up with 6 phase of 30 degrees. And then we have V out here equal to 2 times 1 with a phase of minus 70. So that'll be 60 minus 70. So that is added together. So we end up with 2, minus 10 degrees. And you can see here, that's what we got here on the answer below. 12 volts DC plus 6 cosine 2000 pi t. So let me just highlight it here with a little pointer. So the first part, we got 12 volts, and then we've got 6 with a phase angle of 30 degrees, but this is at 1000 hertz. So we got the 6 cosine 2000 pi t. There's your 1000 hertz plus the 30 degrees. And then at 2000 hertz, which is the cosine 4000 pi t part, we have 2 volts, so 2 times, but it has a phase shift of minus 10 degrees. So here's just a low pass filter. So how did we get these transfer functions? So again, we have R and we got our capacitor. So it was simply a resistor and a capacitor. This, because we're doing everything in terms of F, because it's truly it's when you think about signals, everything is in relation to hertz. So it's 2 pi F. So this is just 1 over j omega c. So that's the impedance. So we've replaced omega with the frequency. So 2 pi F. V in over V out. So we go ahead and we would write this. So the current going through this, doing mesh analysis, is equal to V in. So we've got that with times, we have the resistance R, and we have the current going through the capacitor, which is the 1 plus j omega with j over omega c. So this times the current equals V in. So that gives us our current I. V out is just I times this component. So we have V out is I times 1 over j omega c, or 2 pi f. So putting this equation and this equation together, we end up with this. And of course, then if we want to know V out over V in, then we're just left with, taking doing the algebra in this, V out over V in is just 1 over 1 plus j omega RC, or 1 plus j 2 pi f RC. So 1 plus j 2 pi f RC. Now, the useful thing is we want to talk about cutoff frequency. So where that's basically, we want to know where how F going through, and there's going to be some cutoff frequency in which this filter cuts off. And again, I said I'm going to show you here in just a moment, as this lecture concludes, what this looks like. But what we end up with is simply, like I said, we end up with at a fundamental level, if this is FC, then everything here is passed through, and then everything here is cut off. So this is pass and then off. So this becomes 0. And this is just, we'll just put a 1 here that is just cutting through. So the idea is if and another phrase for this is also known as FB, or the break frequency. different conventions. I think the book might use FB. I usually use FC for cutoff. That's more common. So you have that, and this is just simply 1 over 2 pi RC. In other words, the time constant of the function. That is the cutoff frequency. By doing this, you're able to just simply know what FC is in terms of hertz, and you get this feeling of you don't have to constantly compute 1 over 2 pi RC. You just call this whatever the frequency is. You know, the cutoff frequency is at 1,000 hertz. Once you know that, then you can work your transfer function. The useful thing about this is that usually you're trying to set the frequency cutoff to a specific frequency. So you're going to want to create your filter to set to some FC. So plotting all of this, we end up with h of f and the phase. We can plot this and we get something that looks like this, where if you take the magnitude, and remember the magnitude is the magnitude component of the frequency, you would end up getting an equation that looks like this. And then, of course, the phase is just the arctan of f over fc. Of course, it's negative because of the negative sign in the function. So you can go through the mathematical process of determining h of f, but this is what it works out for the low-pass filters. So for high-pass filters, I won't go through this in as much detail. You can run through the math as well. It's just basically the same process. And of course, you can do these with inductors as well, and just change the position of where the inductor is or the capacitor is. In the case of a high-pass filter, you put the capacitor in place where the resistor was, and the resistor is now where the capacitor was. And of course, it's completely inverse if you want to use an inductor. So here, same thing. The cutoff frequency is the same, except because of the way the math works out, it's really a cut on frequency. In other words, it cuts off everything below the frequency and it passes everything above the frequency. And so the transfer function on this is just j over f over fc, 1 plus j over f of fc. And then we end up with our transfer functions in the sense of magnitude and phase look like this. And it's just notice how the phase shift occurs as we go from 90 degrees, and it will eventually asymptotically will reach 0 degrees. And how the magnitude goes from 0 degrees, it's about 0.707 which is known as a 3 dB point, which we'll cover that in another topic. And you asymptotically will reach 1 as the frequency eventually goes all the way up. So, okay, let's just, now that we've discussed these actual transfer functions, just to kind of sum everything up, we have these 4 different filters. So ideally, graphically, it looks like this. Ideally, you would have the magnitude of a low pass filter be 1, up to your cutoff point, f of h in this case, or f of c, and then after you hit that point, it is completely 0. So it is like a square function up into the moment of the cutoff frequency. High pass filter is the exact opposite of that, is we turn on at some low frequency set point, the cut on frequency, and then from there it is just a magnitude of 1 and just will completely pass as needed. Band pass filter has both a low and a high frequency and will cut on and then cut off. Anything below is 0, anything above is a 0, and anything between the two is a perfect 1. And band reject, or a notch filter, is the inverse of the band pass, where it passes everything below low and anything above high, but anything between the low and high cutoff frequency ranges is a 0. And that sums everything up. So in summary, I know this was a little bit of a long topic. Today we talked about using Fourier series, kind of quick introduction of what that is and why we're studying frequency response, and how everything that you learn with phasors, everything you've done so far with frequency analysis or frequency AC signal analysis now corresponds to frequency analysis and frequency response. So we've given an introduction of that, 2-port networks, an input and output, and then coming up with a transfer function for a specific circuit, and what transfer functions look like, their magnitude and their phase. So when we also talked about common filters that are used in instrumentation and processing, which is the low pass, the high pass, the band pass, and the notch filter, also known as the band reject. Please come to the Q&A session to get a little bit more detail and us talk about working a few problems and stuff. Anyway, we'll have a wonderful day.